Welcome, I'm Kirk Weiler, and today we'll be examining the behavior of cubic polynomials in Math 4 Honors. Now, throughout the lesson today, I want you to keep one thing in mind, which is that all the techniques that we're developing today for cubic polynomials work on any functions. The beauty of cubics is that they're the simplest curve that really requires calculus to get a good sense for what they look like. Unlike quadratics, where we can find turning points using the classic negative b divided by 2a formula, cubics require more tools. Let's take a look at exercise number 1. In this exercise, you're asked to graph two cubics using your graphing calculator in a specified window. Hit pause on the video right now, graph both of those, and do little sketches of them under exercise 1. Alright, let's talk about what the purpose of exercise 1 was. In exercise number 1, what we really wanted to do was review the two basic ways that cubics can look. A cubic can either have 0 turning points, or it can have 2 turning points. This is very different than from a quadratic. In a quadratic, we basically have one turning point and either concave up or concave down. Somewhat boring. Cubics are a little bit more complex, and that's where calculus can come in to inform us. Before we analyze cubics, though, let's talk about a couple uses of the derivative. Now, make sure that as we go through these uses, you always connect them to the geometry of tangent lines. In the first observation, we notice that the x-coordinate of a smooth turning point will always be a location where the first derivative is equal to 0. Again, this should make all the sense in the world to you. We've got a nice smooth turning point, and we draw in tangent lines at those turning points. The slope is equal to 0. Now, another observation that we can make is simply based on the sign of the first derivative. If the first derivative happens to be positive, then we know that the function is increasing as x increases. And likewise, if the function's first derivative is negative, then it's decreasing as x increases. Using these three facts, we can learn a lot about the shape of any graph, and specifically about the shape of a cubic. So let's take a look at exercise number 2. Here, we're asked to consider a particular cubic function. This cubic function is such that we couldn't analyze it using algebra alone. In letter A, we're asked to find f prime of x. Pause the video now and find the derivative of the function. Alright, let's make sure that we have the correct first derivative before we proceed. F prime of x can easily be found using the power law. The derivative of x cubed is 3x squared. The derivative of negative 7x squared will be negative 14x. And the derivative of minus 5x is minus 5. The derivative of 15 is 0. So there's our derivative function. Remember, for any value of x, this function will give us the slope of the tangent line. In letter B, we're asked to locate all x values where the tangent line is horizontal. Pause the video for a moment and think about what you know about the derivative's value when the tangent line is horizontal. Did you get it? At all horizontal tangent lines, the derivative function, which in this case is 3x squared minus 14x minus 5, the derivative function will always have an output equal to 0. We're going to solve this equation now by factoring. Of course, you could use things like the quadratic formula as well. I tend to be biased towards factoring. It's the first thing that I always look for. It's the quickest thing for me. And it's going to give us roots of x equals negative 1/3 and x equals positive 5. In calculus, we call these critical values, often abbreviated as CVs, locations where the first derivative is equal to 0. Now, in letter C, we're asked to state all intervals where the function is increasing and all intervals where f is decreasing. Notice both of these things are really a geometric description of what the function's doing, but we're going to translate them into an algebraic inequality. To have the function increasing means for the first derivative to be positive, and likewise for f to be decreasing, the first derivative will be negative. So, and this may not thrill you, but that means that we're solving an inequality. We're really going to solve two inequalities and do it all in one analysis. We're going to look at how the first derivative plays out along a number line. Now, if we want to know where the first derivative is positive and where it's negative, it's really great to know where it's equal to 0. But we already have that from part B. We know at x equals negative 1/3 and at x equals 5, the first derivative is 0. So what we're now going to be doing is picking x values that are within the interval negative 1/3 and 5, and x values on the outside, and test them in our derivative. Let's pick an x value in here. Let's go with our favorite, x equals 0. Now, there's no question that we could substitute that into our derivative equation right here. But the vast majority of times, if we want to evaluate a derivative and we have it in factored form, it's best to just substitute it into that. And we'll see why in just a moment. So if we take x equals 0 and we substitute it into 3x plus 1, we get a positive. And if we substitute it into x minus 5, we get a negative. A positive times a negative obviously gives us a negative, and that means that the original function f must be decreasing. A lot of times students will put a little not f prime, but f of x down here so that we understand what that arrow is telling us. Now, if we take an x value out here, let's say x equals 6, and we substitute that into the first parentheses, we have a positive. Into the second parentheses, we have a positive. And a positive times a positive, of course, gives us a net positive. That tells us that the function is increasing in this interval. We can pick one final x value. Let's say x equals negative 1. Substituting it, we'll get a negative, and a negative, their product being a positive. If you don't understand the sign analysis, take a little bit of time to think about it right now. We do have to answer the final question, even though the number line seems to really indicate what's going on. It asks us for intervals where f is increasing and where f is decreasing. I'm going to just do the increasing one. I'll leave the decreasing one for you to write out. But we're going to say that the function is increasing, put a little colon, on the interval negative infinity, all the way up to negative 1/3, and then it picks up increasing again from 5 up to infinity. We should always give a piece of information that justifies that. In this case, it's because f prime is greater than 0. You could likewise make a statement about it decreasing from negative 1/3 to 5, because f prime is less than 0. Now, letter D, we're going to finish off here by trying to figure out where we have a relative maximum and where we have a relative minimum. Those are turning points. That's probably pretty darn obvious just from the sign analysis what this cubic looks like. Kind of looks something like that. So it's pretty obvious we have a relative maximum here, a relative minimum here. So really, it's just about justifying it. And I'm going to write down the justification for that relative maximum at negative 1/3. Here's what we want to write. X equals negative 1/3 is the location of a relative max. Here comes our justification. Because f prime changes from positive to negative. It's the location of a relative max because the slope, f prime, changes from positive to negative. Now, a lot of students want to say it's the location of a relative maximum because the function changes from increasing to decreasing, and this is certainly true. But in a certain sense, it's missing the point. See, the point of calculus is to use an algebraic quantity, an output, a numerical output, like the value of the derivative, to tell us something about the graphical nature of the function. To say that it's a relative maximum because it goes from increasing to decreasing, the function that is basically saying it's a relative maximum because it's a relative maximum. So we're always going to be using information about the derivative to justify what features we have on the graph. In exercise number 3, they give us a new cubic and they ask us to determine the locations of all relative maximum and minimums. And then we're going to justify our answer using the derivative. So hit pause on the video now and take up to 5 minutes to think about this problem. Take the derivative, find out where you have horizontal tangent lines, draw out a number line of f prime, think about what it tells you, then try to determine where we have those maximums and minimums. Hit pause now. Okay, let's do the analysis. This is a little bit of a lengthy analysis, and we have to kind of put everything together. The first thing I very much hope is that when you saw that negative x cubed divided by 3, that you didn't use the quotient rule. You can, but it takes a long time, and what I've always found is that it introduces errors for students. It confuses them, and it takes too long. So I'm just going to recognize that that's a power function, and I'm going to find its derivative by just bringing the 3 down, multiplying it by the negative 1/3, and getting negative 1. So much easier. So I get negative x squared minus 4x plus 12 is my first derivative. Alright, now in order to find my horizontal tangent lines, I'm going to set that derivative equal to 0 and solve. So I've got negative x squared minus 4x plus 12 equals 0. A lot of students right now, very understandably, have the urge to divide both sides of the equation by negative 1 or multiply in order to get rid of the negative 1 coefficient on the x squared. Totally understandable. But I'm going to keep that negative 1. And I'm going to keep it because it really makes a difference in terms of not the solutions to this equation, but in terms of how I think about the first derivative of the sign analysis. I'll explain all of that in just a minute. So I'm just going to do what I always do when I solve a quadratic by factoring. Just going to keep factoring until I see factors that allow me to come up with the roots. So here we have it. X equals negative 6 and x equals positive 2. Okay, now we're going to do a sign analysis of the first derivative. Why don't we put it right about here on our paper? Alright, I'm going to label it. It's critical that you label your number lines. Critical, critical. No pun intended. Here we've got our critical values, though, of negative 6 and 2. And now what I'm going to do is I'm going to be testing the value of my derivative. But here's the key. I'm going to test it. Oh, let me get the right color on my highlighter. Really want you to understand where we're going to be testing this. I'm going to be testing it. I can't seem to highlight this. We'll get it, I promise. There we go. Nope. And then I highlighted the wrong thing. Here we are. We're going to test it in this factored form of the derivative. See if I can get my pen back. There we go. Alright, so let's say that we take the x value, x equals 0. See, if I substitute it into that highlighted expression, I'm going to get a negative just from the negative 1. Then I'm going to get a positive from the 6. Then I'm going to get a negative from the negative 2. A negative times a positive times a negative, it gives me a positive. If I lose that negative 1, then I think that the derivative is going to be negative there, which it's not. Alright, I can do this for, obviously, 2 other points. Go x equals 3. I could go x equals negative 7. I do find that the sign fluctuates or alternates. Be careful, it doesn't always. But I can see that general shape of the cubic panning out. Again, you make sure that you do that sign analysis. Now I can write conclusions about what kind of features I have and where they're located. Let's come over here and let's talk about x equals negative 6. Right? X equals negative 6 now is a location of a relative, what do we have there? Min, right? And the reason is because f prime changes from negative to positive. Alright, we can say a similar statement about x equals 2 being the location of a relative maximum, but you fill that in. One little comment. Help your math teachers along when you're making these statements. Never, ever, ever, never, ever use the word it. Never do that. Never say x equals negative 6 is the location of a relative minimum because it changes from negative to positive. I know pronouns are nice, we all like them, but the problem with them is that it's not always obvious what they're referring to. Are you referring to the function? Are you referring to the function's first derivative? Little preview, eventually we'll talk about a function's second derivative. So the word it is always very confusing. Alright, let's take a look at the last problem. This one's going to be a little bit harder to do on the video, because what we're trying to do is match the graphs of 4 cubics on the left-hand side with the graphs of their derivatives. This is the first time we've ever done this, and this takes a special kind of thinking that we're going to just start to illustrate today. Alright, take a look at problem number 1, this cubic. I'm going to try to figure out what the graph of its derivative looks like by thinking about values of its derivative. Now remember, the output of the derivative, which will be graphed as the y-coordinate, as its y-coordinate is the value of the slope. So we know at these two x values, the output of the derivative function should be 0. We call them a and b. So somewhere on the graph of the derivative, the output, the y-coordinate, has to be 0 right around those 2 points. Well, a and b actually fit this quite nicely. Shrink down the screen a little bit. Both a and b seem to work well with this description. So which one is the derivative of the function in 1? Well, let's think a little bit about what this function is doing. See, from negative infinity to a, the function is increasing, which means its derivative, f prime, must be greater than 0. In this area, though, the function is decreasing, which means its derivative must be less than 0, and then a derivative greater than 0. So that means I'm looking for a graph over here, right, where the y values are positive, then go to 0, then go negative, then go back to 0, then go positive. Positive to 0 to negative to 0 to back positive again. So this function and this function match up. This is the derivative of this. Let's take a look at graph number 2 and see what we can tell about that. In this particular graph, the cubic is one that has no turning points. In fact, it's always increasing. And what that tells us is that its derivative will always be greater than 0. Its y values will always be above the x-axis. Now granted, they're increasing faster here and here, right? So the slopes are very large and positive, becoming less large and positive, and less large and positive, then growing again. So we're looking for a function that always stays positive, but is smaller and smaller, and then gets larger and larger. That's right here, right? All positive values, but values that are getting smaller and then getting larger. So letter C is the derivative of the graph of number 2. Alright, I think we'll end there for now. Thank you for joining us. Until next time, keep thinking and keep asking questions.